Okay, so I hope you were able to do this functional derivative. Let's do it together. Well, just by the usual rules of functional differentiation, what we know is that when we differentiate this exponential, we're going to get the exponential back. So we'll get the integral d4x, j of x, phi of x, and then we'll get the derivative of the exponent. So, well, integral d4x will be left alone. The derivative doesn't do anything to that. Now, the delta of j of x with respect to j of x1 is a four-dimensional delta function of x minus x1. And then the functional derivative doesn't act on phi of x at all. And then that integral is very easy to do. The delta function just sets x equal to x1. So we'll end up getting phi of x1 times by the integral d4x j of x phi of x. Now, the same logic extends if we consider a string of derivatives. So let's imagine that we were taking a derivative with respect to j of x1, then a derivative with respect to j of x2, and so on, all the way up to a derivative with respect to j of xn of the exponential. Okay, so if we take these derivatives, let's just simply write out one step. Maybe this is a useful thing. J of x1, then we'll have delta j of xn minus 1. And now let's write down what derivative with respect to j of xn would have been. Well, from the example that we've just calculated, we know that that functional derivative acting on the exponential will give us phi of xn multiplied by the exponential again. Integral d4x j of x phi of x. Now, phi is a constant as far as derivatives with respect to j goes. So when we come to calculate the derivative with respect to j of xn minus 1, it'll slip straight past the phi and simply act on the exponential. And then we are just again recycling the example that we just did. So, and we can repeat that then for j of xn minus 2 and so on, all the way up to j of x1. So the rule is that each of these functional derivatives is simply replaced by a phi evaluated at the same point. So that's the answer that we get for taking these n functional derivatives. So great. Okay, so let's maybe just separate these two formulas. So here was one formula over here. This was with a single field. And then we just extended that to argue that a very, very similar result, essentially the same result, holds even when we take derivatives with respect to n fields. Good. Now, what do we actually want to do? Well, we actually want to take derivatives of z of j. So let's try to do that now, and let's see what happens. So when we come to taking derivatives of z of j, we've got delta j of x1 all the way up to j of xn on z of j. And now let me just write out z of j just to remind you what z of j is. So we'll have an integral d phi, so that's the normal path integral measure. Then we've got e to the is plus an integral d4x j of x phi of x. Now, these functional derivatives, they are all derivatives with respect to j. So it's j that we're differentiating with respect to. If we look on this side of the formula, where is the j dependence? Well, there's no j dependence in the path integral measure. There's no j dependence in the action. So all of the j dependence sits only up there in the exponential. So I can take these functional derivatives into the path integrals. I can take them past that measure. It doesn't act on the e to the is. All it does is act on the exponential term. And we've just had some experience in calculating what that gives. So we'll have an integral d phi. We just pull all of the derivatives past this path integral measure, no problem. We don't act on e to the is, we act on the exponential. We know exactly what that's going to give us. This is phi of x1 up to phi of xn, which I didn't need to open in bracket. Let's just remove that. And then we have e to the is plus an integral d4x j of x phi of x. Great. And now all that I want to do to establish my formula is I wanted to set j is equal to 0. Take those n derivatives and set j is equal to 0. So if I now set j is equal to 0, well, it's pretty simple. Setting j is equal to 0 means I've still got an integral d phi. Setting j is equal to 0 does nothing to my path integral measure. It does nothing to my product of fields. I've got e to the is, and then that second term vanishes because I've set j is equal to 0. So this is the formula that we have managed to derive, okay, just by functional differentiation. And if you look at what we had, that path integral is just the correlation function, the time-ordered correlator, okay? So that's what we've gotten here. And that means we've proved this formula star. So we've managed to prove this formula star that we had. And this is the reason why z of j is an interesting quantity to calculate. Now, I want to remind you of one other thing, and that is that, oh, let me just improve this a little bit. That's better. I want to just remind you of one little thing. You know, I of naught is also I with b is equal to 0. Okay, and that maybe makes it look a little bit more symmetric. Good. Now, to calculate IB, all that we needed to know is what was I naught, and we calculated it by doing a shift. It seems reasonable to expect, and later on we'll prove it, that to calculate z of j, all that we need to know is what is the value of z of naught. Do we know the value of z of naught? Well, okay, so let me just extend this formula slightly. This now I'm filling in that we know by our master path integral formula that this was actually the time-ordered correlation function of n scalar fields. Okay, so I want you to remember that. Now, let's see if we can work out what is z when j is equal to 0. Okay, so z when j is equal to 0 is nothing but the integral d phi e to the is, and that's it. Because remember, z of j was integral d phi e to the is plus integral d4x j of x phi of x. If we set j is equal to 0, then z of naught is just integral d phi e to the is. Okay, so that's what we have for z when we set j is equal to 0. Looking at the blue boxed formula just above it, what is this equal to? Well, this is bra vacuum, we've got no fields, and Ket vacuum. So this is just the overlap of the vacuum with itself. So this just fixes the normalization of the vacuum, and we will set this equal to 1 as usual. By making this choice, we picked a single number, and you can think that we are normalizing the measure of our path integral, okay? So this is a perfectly valid thing to know or to do. So in fact, we know what the value of z with j is equal to 0 is. But if we know what the value of z with j is equal to naught is, you know, we expect, based on our experience with the 1D problem, that we should be able to evaluate able to compute z of j, that part. And in fact, that's what we're going to do next. I'm going to try to prove to you that we can do it. We're going to do things exactly as we did the 1D integral. So you should know what that means. Just to remind you, what does that mean? Well, we're going to start off with, before we started off with I of b, so now we're going to start off with z of j. And then we did a shift of the integration variable x to make I of b look like I naught. So we're going to start with z of j. We're going to do a shift of the integration variable phi to make z of j look like z of naught. And then we'll use the value of z of naught to write down what the value of z of j is. That's what we're going to do next.